Okay, hello everybody. My name is Jacob Payne, and today I will be presenting problem 5.17 for the bonus work assignment. Problem 5.17 states that a large parallel plate capacitor with uniform surface charge sigma on the upper plate and negative sigma on the lower plate is moving with a constant speed v, as shown in figure 5.43, which I've drawn in the upper left-hand corner. Part A is to find the magnetic field between the plates and also above and below them. Part B is to find the magnetic force per unit area on the upper plate, including its direction. And part C is at what speed v would the magnetic force balance the electrical force. Okay, so starting with part A, we will be identifying a few different things. First of all, if we are looking at this plate from the y direction, we're going to be seeing currents coming right at us, in the positive y-axis direction. So that being the y direction. What we can do is use equation 5.44, which states that the closed path integral of b dot dl is equal to mu naught I enclosed. What we can do is we can use an Amperian loop around this current where this distance is L. And we would have that B times 2L is equal to mu naught I enclosed. Now, I enclosed, if we have a surface charge, sigma, traveling at a speed v, then our surface current is sigma v. In this case, we are calling the direction of v y hat. So now the current enclosed is just K times L. So K times L. If we solve for B, we have B is equal to mu naught K over 2. Now that is the magnetic field from one of these plates. And so what we're going to have to consider now is the fact that we have two plates, one with a current in the positive y direction, one with the current in the negative y direction. So if we follow this kind of method here, if we go back to the Amperian loop, by using the right-hand rule, the magnetic field above the current will be in the negative, no, sorry, the positive x hat direction, and below will be in the negative x hat direction. So that being the case, above plate 1, we have that the B field from the top plate above both plates is equal to mu naught K over 2 x hat. Now the B field from the bottom plate above the plates is the same magnitude, but the opposite direction. since it is the opposite direction of the current. In the middle, we have that the B field from the top in the middle is equal to mu naught K over 2, and that is in the positive X, or sorry, the negative X hat direction. And the B field from the bottom plate in the middle is also negative mu naught K over 2 X hat. As you would imagine, B field from the top plate below is negative mu naught K over 2 X hat, and the B field from the bottom plate below is equal to positive mu naught K over 2 X hat. So if we find the magnetic field above, middle, below, the magnetic field above is equal to the magnetic field below, which is 0. Since they have the same magnitude in opposite directions, they will cancel each other out. The magnetic field in the middle is equal to negative mu naught K X hat, which, remember, K is sigma V. So that is the solution to part A. Part B, as we recall, is find the magnetic force per unit area on the upper plate, including its direction. So from equation 5.24, we know that the magnetic force is equal to the integral K cross B the integral dA. Now, what we're looking for is the unit, the magnetic force per unit area. So what we can do is we divide the force by the area, and we will get just K cross B. Now, if we recall, K is, go back to sheet 1. K is sigma V y hat. Cross the B field from plate 2, B field from plate 2 on plate 1 is going to be mu naught K over 2, mu naught K over 2. And that is in the X hat direction. Sorry, in the negative X hat direction. When we find this cross value, we have K is sigma V, as we recall. So we have negative mu naught sigma squared V squared over 2 y hat cross x hat. Now y hat cross x hat, we go in this order. Y hat cross hex hat is going in the reverse order, so it's going to be negative z hat. Mu naught sigma squared v squared over 2 z hat. So the force per unit area on the upper plate is mu naught sigma squared v squared over 2 in the z hat direction. For part C, we are asked at what speed would the magnetic force balance the electrical force? Well, we know that the electrical force on a conductor is equal to sigma squared over 2 epsilon naught, and it's in the n hat direction. So it is perpendicular to the surface. Sorry, this is the force applied from an electric field. That's the force per unit area of the conductor. So we're trying to find the force on the top plate, seeing as that we already have the magnetic force from the bottom plate on the top plate. So the magnetic force from the bottom plate is going to be sigma squared over 2 epsilon naught in the positive z direction. Sorry, in the negative z direction, because it is the opposite sign. We know that the magnetic force per unit length, or per unit area, is going to equal the magnitude of the electrical force per unit area. So we have, going back to part 2, we have mu naught sigma squared v squared over 2. Mu naught sigma squared v squared over 2 is equal to sigma squared over 2 epsilon naught. We can do some cancellations, and we end up with square root 1 over the square root of mu naught epsilon naught. If we plug that into a calculator, we get 2.999 times 10 to the 8th meters per second as the velocity that the charge carriers would need to travel in order for the magnetic force to balance out the electrical force. That will be all for today. If you have any questions, please let me know.